Humanity has always gazed at the stars, dreaming of visiting distant worlds. But even our closest neighbor, Proxima Centauri, is over 4 light-years away, an impossible journey with current rockets. The speed of light is the universe's ultimate speed limit, keeping us confined to our solar system. That's why the idea of faster-than-light, or FTL, travel is so captivating. Imagine reaching another star system in weeks, not millennia. NASA recognizes this potential and is seriously investigating the physics behind FTL travel. They're not building starships yet, but they're taking the first steps to see if it's possible. The quest for FTL travel pushes us to rethink space, time, and energy. Every leap in human history began with a bold idea that seemed impossible. NASA's research is about laying the groundwork for future generations who might one day call the galaxy home. But how could we break the speed limit? Einstein's relativity says nothing with mass can travel at light speed. Trying would require infinite energy. But what if we could make space itself move? That's the core idea NASA scientists are exploring. This is where the concept of a warp drive comes in. In 1994, physicist Miguel Alcubierre, inspired by Star Trek, wondered if a warp drive could exist within real physics. Studying Einstein's equations, he realized they didn't forbid a shortcut through space. Alcubierre proposed a model where a spacecraft could travel faster than light, not by moving quickly, but by moving a piece of space-time itself. Picture standing on a rug. Instead of walking, you pull the rug toward you and ride along. The ship inside the warp bubble wouldn't move relative to its local space. Instead, space in front contracts and space behind expands, propelling the bubble forward. This loophole doesn't break the laws of physics, it bends them. Alcubierre's model is mathematically sound within general relativity. It's not easy to build, but it shows warp drives aren't pure fantasy. The idea gave scientists a theoretical playground to explore FTL travel. It provided a blueprint for researchers, including NASA, to analyze and improve. For the first time, FTL travel had a foundation in real physics. The Alcubierre drive became the first serious scientific look at interstellar travel. It changed the conversation from fiction to possibility. Let's look closer at how a warp bubble works. Imagine space-time as a calm ocean. A ship can only go so fast unless it rides a wave. The warp bubble is like a self-generated wave in space-time, carrying the ship along. The spacecraft sits inside, not moving through space but being transported by the distortion. To create this, the drive contracts space-time in front, pulling the destination closer. Simultaneously, it expands space-time behind, pushing the starting point away. The result, the bubble moves and so does the ship inside. From the crew's perspective, there's no acceleration or crushing forces, just a smooth ride. They're not moving relative to their local space. The universe is moving around them. This sidesteps Einstein's speed limit. Nothing moves through space faster than light. But space itself can expand or contract at any rate. After the Big Bang, the universe expanded faster than light. The Alcubierre drive would harness this principle on a small scale. It creates a pocket of expanding and contracting space-time to propel itself. The bubble doesn't break the light speed barrier. It takes a shortcut. It's a radical new way to think about travel. The theory is beautiful, but there's a huge catch: negative energy. To warp space-time, the Alcubierre drive needs a ring of negative energy or negative mass, something far stranger than antimatter. Negative energy would have repulsive gravity, pushing things away. It's the essential fuel for the warp engine. The problem? We don't know if negative energy exists in a usable form. It appears in quantum physics, but only in tiny, fleeting amounts. The Casimir effect can create a region with lower energy than a vacuum, a form of negative energy, but only on a microscopic scale. Alcubierre's original calculations required negative energy equal to Jupiter's mass, an impossible amount. Later research reduced the requirement, but it's still astronomical. No one has ever created or stored negative energy in the lab. Finding a stable, scalable source is the central puzzle for NASA and physicists worldwide. Without it, the warp drive remains theoretical. The search for negative energy is the biggest hurdle in making FTL travel a reality. Until we solve this, warp drives stay in the realm of speculation. But the quest continues. Despite the negative energy challenge, NASA hasn't given up. At EagleWorks Laboratories, Dr. Harold "Sonny" White's team is taking the first steps. They're not building starships, they're testing the physics in the lab. By tweaking the shape of the negative energy ring, they've reduced the energy needed from planetary to spacecraft scale. Using a warp field interferometer, they try to detect tiny spacetime distortions with lasers. Even a change smaller than an atom's width could be significant. They're also studying the Casimir effect, creating custom cavities to see if negative energy can be controlled or amplified. These experiments are at the cutting edge, probing the secrets of space-time. The work is slow and painstaking, but each result brings us closer to understanding. NASA's team is turning theory into testable science. It's a small but crucial step toward the stars. Progress at EagleWorks is exciting, but the road ahead is daunting. The main obstacle remains: negative energy, how to produce or store it in large, stable amounts. There are other issues. A warp bubble might accumulate deadly radiation, and controlling or steering it is a huge unknown. Building a machine to manipulate space-time would be the most complex engineering feat in history. Even with breakthroughs, turning theory into a working engine could take centuries. Many physicists remain skeptical, pointing out that the math relies on unproven physics. NASA's research is speculative and long-term, not a funded mission, but the potential payoff unlocking the galaxy is too great to ignore. It's a high-risk, high-reward endeavor. Some researchers are exploring a more practical path-positive energy warp analogs. These models use only regular matter and energy, no exotic physics. They can't create true FTL bubbles, but they might enable slower-than-light warps. A subliminal warp drive could push against space-time itself, allowing continuous acceleration without massive fuel. This could revolutionize propulsion, making high-speed travel within the solar system possible. Studying positive energy effects lets scientists test their models in the lab. These experiments are valuable stepping stones, refining our understanding of energy and gravity. It's progress, even while the biggest puzzle piece is missing. Warp drive research is opening new frontiers in space travel. Even if FTL remains out of reach, the science could lead to breakthroughs in propulsion. Reactionless drives, inspired by warp theory, could make trips to Mars or the outer planets much faster. The advanced physics being explored might yield new energy sources, materials, or ways to manipulate gravity. Fundamental research often leads to unexpected technologies, just as quantum mechanics led to lasers and computers. The quest for a warp drive is about expanding our understanding of the universe. Even if we never break the light-speed barrier, the journey will make us a more advanced civilization. The tools and insights gained will benefit science far beyond space travel. NASA's exploration of FTL travel is bold and forward-thinking. Alcubierre's model showed FTL might be possible by moving space, not the ship. The biggest challenge is negative energy, an ingredient we haven't yet found. Despite this, NASA's EagleWorks lab is making real progress, reducing energy requirements and testing for warp effects. Their work with the Casimir effect links theory to experiment, step by step. The dream of interstellar travel is still distant, but the conversation has moved from fiction to real science. NASA's research is a testament to humanity's curiosity and drive to reach the stars. The journey has just begun, and the quest itself will expand our horizons. Even if the destination is uncertain, the pursuit will enrich our knowledge. The stars are waiting, and we're determined to find a way.